Hello folks, and welcome to this lesson on Gibbs energy and electrochemistry. By the end of this lesson, you should be able to use standard reduction potentials and other information about a redox reaction to calculate the Gibbs energy of the reaction. So we've already talked about the fact that when you have a redox reaction, sometimes they'll happen spontaneously, sometimes they're not. You've already looked at whether a redox reaction will happen spontaneously by looking at those E0 of an overall cell value. And when you get a positive E0 value, you know that it's going to happen spontaneously. Well, you can also use these values to help you calculate the Gibbs energy, because sometimes knowing that Gibbs energy can be very useful. So the equation in question is this. So basically, you are going to attach that negative sign to it because remember, your positive E0 values mean spontaneity, but in terms of Gibbs energy, it's negative values. So you're going to toss that negative sign on there. You're going to look at how many electrons are transferred in your balanced redox equation. So remember, when you're balancing your redox reactions, you have to take your half reactions, make sure all your electrons cancel out, and then you come up with the final balance equation. So that number of electrons that you will end up canceling out is what you're going to put in here. And then to make this all into an equation, you're going to use Faraday's constant, which is 9.65 times 10 to the power of 4 coulombs per mole. Now, how do all of the units work out with everything that's in here? Well, we're looking at number of electrons, so that one doesn't really have a unit to it. But we have your coulombs per mole from the Faraday constant, and then your E0 value has volts. Now, volts is actually joules per coulomb, and so if you insert that into here, cancel out what gets canceled out, you end up with joules per mole for this value. Now, if you need to use delta G values to be able to find out whatever else, make sure that you are using those unit conversions. Your delta G values in references are typically going to be in kilojoules, so make sure that all works out. So let's say you're calculating the Gibbs energy for a cell made with aluminum and zinc in standard conditions. So if we are going to be making a voltaic cell with this, you're going to have your aluminum metal, and then you're going to be using zinc ions. So in this particular case, our half reactions are going to be as follows. Now, to get a properly balanced redox reaction out of this, we're going to need to take this equation, multiply it by 2, and take that equation and multiply it by 3. So here you can see that when you have that balanced redox reaction, you're going to have a transfer of 6 electrons. So now let's figure out the Gibbs energy. We're going to take the 6 that we found out for our N. Faraday's constant is Faraday's constant, and for the E0 of the cell, we're going to take those values from your tables. This one is the oxidation, so don't forget it needs to be flipped, and then this one is the reduction as it is, so you're going to use that value as is to find out what the E0 of the cell is. When you do this, and you do that conversion from joules to kilojoules, you should find that the delta G for this particular cell will end up being 521 kilojoules per mole. And that's about it. You might be expected to find other values using this equation, not necessarily always delta G all the time, but at that point it's all math. That's the end of this lesson. I'll see you next time.